Our universe holds secrets that make our laws of physics seem like suggestions. We are about to embark on a journey through 30 cosmic discoveries that completely defy logic, each one a puzzle that challenges the very foundations of what we think we know. By the end, you will see the cosmos not as an orderly clockwork, but as a realm of breathtaking and bewildering mysteries. We will encounter a force dragging entire galaxies toward an unseen horror, and a silent star that flickers as if something massive is passing in front of it. What do you believe is the universe's most baffling secret? Our journey begins with a destination we cannot see, a force we cannot escape. The first discovery is the Great Attractor, a point in the cosmos that is pulling our entire Milky Way galaxy, along with hundreds of thousands of others, toward an unknown fate. Picture the universe as a vast flowing river of galaxies, all moving in a grand cosmic dance. For decades, astronomers mapped these motions and noticed something deeply unsettling. Every galaxy in our local supercluster, including our own, is not drifting randomly. We are all being swept with immense speed toward a single region of space. This is not a gentle tug. It is a relentless, powerful pull from something with the gravitational force of tens of thousands of Milky Ways. The source of this pull is the Great Attractor. Yet, when we point our most powerful telescopes toward it, we see almost nothing. It lies in the direction of the constellation Centaurus, but it is hidden behind the thick, dusty plain of our own galaxy, an area astronomers call the zone of avoidance. It is as if the universe placed a cosmic blind spot directly in front of the most interesting thing in our neighborhood. For years, this zone obscured our view, making the Great Attractor one of the most frustrating mysteries in astronomy. What could possibly be so massive yet so hidden? As technology improved, allowing us to peer through the dust with X-ray and infrared eyes, we began to see the outlines of the truth. The Great Attractor is not a single monstrous object. It is an unimaginably dense knot of matter, a gravitational focal point where thousands of galaxies have piled up into a colossal supercluster, now called the Laniakea supercluster, of which we are a mere outlying suburb. But here is where logic starts to fray. Even this immense concentration of visible galaxies is not enough to account for the ferocious pull we feel. The math simply does not add up. The visible stuff, the stars and galaxies we can detect, only provides a fraction of the gravitational strength needed to yank us along at over 2 million kilometers per hour. The rest of the force must come from something else, something dark and unseen woven into the very fabric of that region. This means the Great Attractor is not just a place, it is a glaring piece of evidence. It is a cosmic signpost pointing to the overwhelming influence of dark matter, revealing that the hidden skeleton of the universe is clumped in ways we are only beginning to map. We are being hauled toward a shadow, a gravitational ghost of such power that it dictates the motion of galaxies, reminding us that most of the cosmos is made of stuff we will never see. That invisible pull is a humbling reminder of how much we cannot see, but what about the things we can hear? The second discovery is a sound from the void, a whisper so perfect and strange it was literally written in the margins as a cry of astonishment. In the late summer of 1977, a radio telescope at Ohio State University known as the Big Ear was silently scanning the heavens, part of the long, patient search for extraterrestrial intelligence. On August 15th, the telescope's computer printed out a string of alphanumeric data representing signal strength. An astronomer named Jerry Amon was reviewing the printout days later when his eyes locked onto a sequence of characters so extraordinary he circled it in red pen and wrote one word beside it. Wow! For 72 glorious seconds, the telescope had recorded a powerful, narrowband radio signal bursting out of the silence. It was not static, not a natural cosmic object like a pulsar. It was concentrated on one specific frequency, 1420 megahertz, a frequency protected by international agreement because it is the natural emission line of hydrogen, the most common element in the universe. It is considered a logical channel for anyone wanting to be heard, a cosmic hailing frequency. The signal rose to incredible intensity and then faded away as the Earth's rotation moved the telescope's gaze past it, exactly as you would expect from a distant, fixed point in the sky. It came from the direction of the constellation Sagittarius, and then it was gone. In the decades since, that patch of sky has been scoured by telescopes around the world, listening intently for a repeat, for another whisper, for anything. The silence has been absolute. The wow signal was never heard again. This single event defies easy classification. It was too clean, too perfect to be any known natural phenomenon, yet its one-off nature makes it impossible to verify. It sits in a haunting limbo, the strongest candidate we have ever received for a signal not made by human hands, a 72-second shout into the cosmic night that we happen to be listening at exactly the right place, at exactly the right moment. Was it a fleeting message, a beacon sweeping past us, or something else entirely? The enduring power of the wow signal is not in the answer it provided, but in the profound question it etched permanently into our consciousness. We heard something that sounded like a call, and we have spent every moment since wondering if anyone was actually on the other end of the line. The silence that followed the wow signal is a different kind of message, one that speaks to the vast, empty stretches between the stars. But what if the emptiness itself is moving? Our third discovery suggests that even the largest structures we can see are caught in a current they cannot resist, a current flowing from a source we can never observe. Astronomers call this the dark flow. For years, scientists have meticulously mapped the motion of galaxy clusters, the titanic cities of stars that are the largest gravitationally bound structures in existence. According to our best models of the universe, these motions should be random, a gentle and chaotic drift left over from the Big Bang. Yet, when researchers studied the subtle shifts in the cosmic microwave background, the ancient afterglow of creation itself, they found something impossible. Hundreds of galaxy clusters, each containing thousands of galaxies, are not drifting aimlessly. They are all streaming like leaves caught in a cosmic river in the same direction. They are moving at a staggering speed of over 2 million miles per hour toward a specific point in the sky, a point that lies far beyond the edge of everything we can see. This is not the Great Attractor's pull, which is a local phenomenon. This is something else entirely, a flow on a scale so immense it defies all conventional explanation. Think of the observable universe as a sphere of light with us at the center. Everything we can possibly see or interact with lies within this sphere. The source of the dark flow lies outside of it, beyond our cosmic horizon. This presents a fundamental problem. According to the standard laws of physics and cosmology, nothing, not even information or gravitational influence, can travel from outside the observable universe to inside it. The speed of light sets an absolute boundary, yet the dark flow acts as if something unimaginably vast, a structure or a gravitational anomaly of colossal proportions, is out there, tugging on everything inside our visible cosmos. It is as if we are in a boat, feeling the pull of a waterfall we cannot see because it lies beyond the horizon. Some theories suggest this could be the gravitational imprint of another universe, brushing against our own in the greater multiverse. Others propose it is evidence of a pre-Big Bang structure, a scar from the birth of reality that still dictates the flow of matter. The most unsettling possibility is that our entire observable universe is not the main event, but merely a suburb, a small region being pulled toward a much greater mass that lies forever in the unseen darkness. The dark flow is more than a mystery, it is a direct challenge. It tells us that our map of the cosmos is not just incomplete, it may be fundamentally local. The true architecture of reality, with all its sources of gravity and motion, extends into realms we are, by the very laws of physics, forbidden from ever witnessing. If the dark flow is a river pulling us toward an unseen horizon, then our own galaxy holds evidence of a cataclysm that already happened, a pair of scars from a violence we somehow missed. The fourth discovery is the Fermi Bubbles, two colossal orbs of energy ballooning from the heart of the Milky Way. They are invisible to the human eye, but in the high-energy light of gamma rays, they glow like ghostly incandescent bulbs, each one towering 25,000 light-years above and below the galactic plane. Together, they form an hourglass shape 50,000 light-years tall, nearly half the diameter of our entire galaxy. We are living in the aftermath of a galactic-scale explosion, and we did not even know it until the year 2010. That is when scientists processing data from NASA's Fermi Gamma Ray Space Telescope noticed the impossible. The sky map of gamma rays, the most energetic form of light, was not a smooth background. Emanating from the galactic center were these two immense symmetrical lobes, their edges sharp and defined. It was as if we had been living in a house for millennia and only just discovered that the entire structure was built atop the sealed chimney of a titanic furnace. The energy required to inflate these bubbles is beyond staggering. It is equivalent to 100,000 supernovae detonating at once. The source of this fury lies at the very center of the bubbles, at the very center of our galaxy, where a supermassive black hole named Sagittarius, a star, resides. For a long time, we considered this black hole to be relatively quiet, a sleeping giant. The Fermi Bubbles suggest it was not always so. The leading theory is that several million years ago, Sagittarius, a star, woke up. A vast cloud of gas, or perhaps a star that wandered too close, was ripped apart and devoured. But black holes are messy eaters. Not all the material falls in. Some is channeled by intense magnetic fields and blasted outward at nearly the speed of light in two opposing jets, punching through the galactic gas and inflating these colossal cavities. This event would have been a cosmic catastrophe of unimaginable brightness, a beacon visible across the universe. Yet, by the time human eyes looked up, the visible fire had faded, leaving only this lingering high-energy afterglow. But there is a competing and even more puzzling explanation. Some scientists propose the bubbles are not the result of a black hole's meal, but of something far more exotic, the annihilation of dark matter. In this scenario, the dense concentration of dark matter thought to surround the galactic center could see particles of this mysterious substance colliding and destroying each other, releasing the torrent of energy that formed the bubbles. This idea turns the structures from a historical monument into a live experiment, an ongoing reaction that could be revealing the true nature of the universe's dominant, invisible material. So which is it? Are we seeing the ancient echo of a black hole's roar, or are we looking at the glowing signature of dark matter dying in the dark? The Fermi Bubbles force us to confront a humbling truth that our galaxy's quiet, spiral beauty is a facade. It has a violent, energetic heart, and we are only now learning to read its scars. From the violent, glowing heart of our own galaxy, we now turn our gaze outward to a place defined by its profound absence. In the constellation of Boötes, the herdsman, lies a region of space so empty, so desolate, it has earned the ominous title of the Great Void. This is not a simple gap between galaxies. It is a spherical chasm of nothingness roughly 330 million light-years across. To grasp that scale, if you placed our Milky Way at its center, the nearest edge of this void would be over 165 million light-years away in every direction. In a universe we believe is built on a web-like structure of filaments and clusters, the Boötes Void is a staggering hole in the cosmic fabric. Its existence defies our best models of how matter should be distributed after the Big Bang. Gravity, over billions of years, should have pulled matter into a relatively even, frothy distribution, with no gaps larger than about 150 million light-years. The Boötes Void is more than twice that size. It is a cosmic anomaly of silence, For perspective, if the average density of the universe were represented by a handful of sand grains scattered across a football field, the Boötes Void would be a region the size of a city block containing just a single lonely grain. That is the level of emptiness we are confronting. Finding anything at all within this void should be nearly impossible, and yet against all odds astronomers have. Drifting in this immense darkness are a handful of isolated galaxies. The most famous of these is a spiral galaxy with the unpoetic name MCG plus 01020015. It is known as the loneliest galaxy in the universe. Imagine a single, small town with all its lights on, but located in the middle of an empty continent that spans farther than the eye can see in every direction. That is this galaxy's existence. It is so isolated that if you were standing on a planet within it and looked out, you would see almost nothing but pure, unbroken black in your night sky. No neighboring galaxies, no distant smudges of light, just an eternal void. Its very presence is a paradox. How did it form? Galaxies are thought to be born from the mergers and gravitational interactions of smaller clumps of gas and stars. In the emptiness of the void, where there is scarcely any material to gather, this process seems impossible. Did it form in a denser region and get flung into the void by some ancient gravitational slingshot? Or does its existence point to a flaw in our understanding of how structure forms in the first place? The Boötes Void and its lonely inhabitants are a profound challenge. They force us to question whether our picture of the cosmic web is correct, or if the universe allows for deserts of a scale we never thought possible. It is a reminder that sometimes the most baffling thing in the cosmos is not what is there, but what is not. That profound emptiness is a mystery of absence, but some cosmic puzzles are defined by their strange, flickering presence. In the constellation Cygnus, a star named KIC 8462852, but better known as Tabby Star, behaves unlike any other we have ever seen. Its light does not shine with a steady, predictable rhythm. Instead, it dims in bizarre, dramatic, and utterly irregular ways, as if something colossal and incomprehensible is passing in front of it. The story begins with the Kepler Space Telescope, a mission designed to find planets by watching for the tiny, periodic dips in starlight that occur when an orbiting world transits across its sun. Kepler observed over 150,000 stars, and among all that data, Tabby Star stood out as a profound anomaly. Astronomer Tabitha Boyajian, who led the team studying it, found light curves that defied all logic. Most stars with planets show dips of perhaps 1%, lasting a few hours. Tabby Star experienced drops in brightness of up to 22%, and these dips lasted for days, even weeks at a time. The patterns were not periodic, they were chaotic, with no repeating schedule a planet or even a family of planets could possibly create. One particularly astonishing event saw the star's light plummet by a staggering 15% in just a single day. To block that much light, whatever was in front of the star had to be enormous, covering nearly half of its surface. The immediate and most tantalizing theory was one of cosmic engineering. Could these be signs of a Dyson sphere, or more likely, a swarm of Dyson swarm structures built by an advanced civilization to harness the star's energy? The irregular pattern could suggest a partially constructed swarm with vast collectors orbiting in a chaotic cloud, intermittently blocking our view. This idea captured the public imagination, turning Tabby Star into a modern icon of the search for extraterrestrial intelligence. Scientists, however, are trained to seek natural explanations first, and they proposed many. A huge, fragmented swarm of comets, thousands of them, could perhaps explain some of the dimming if they were on wildly eccentric orbits, releasing immense clouds of dust and debris. Others suggested intrinsic stellar variability, that the star itself was undergoing strange, never-before-seen convulsions. Perhaps it was recovering from a catastrophic collision with a planet, surrounded by a vast, clumpy disk of leftover debris. Each explanation, however, ran into serious problems. A comet swarm large enough to cause the deepest dimmings would require more comets than exist in our entire solar system, and the dust from such events should glow in infrared light, which we do not see in sufficient amounts. The star itself appears otherwise normal, not showing the pulsations or outbursts that would accompany such dramatic internal changes. Years of intense observation have followed, from professional telescopes to crowdsourced networks of amateur astronomers. The star continues to dim, sometimes in slow, subtle trends over years, other times in sharp, unpredictable plunges. Each new dip provides more data, but also more confusion, ruling out some models while failing to confirm any single one. Tabby Star remains a stellar enigma, a beacon of pure mystery. It forces us to confront the limits of our stellar knowledge. We have catalogued billions of stars, yet here is one, seemingly ordinary in every way except for the shadow play it performs. Is it a natural phenomenon we simply have not witnessed before, a new chapter in stellar physics waiting to be written? Or is it something else, a signature so advanced it appears to us as magic or as chaos? For now, the star keeps its secret, flickering silently in the dark, a reminder that sometimes the most compelling mysteries are not found in the voids, but in the very lights we thought we understood. The silent, flickering mystery of Tabby Star forces us to question what we know about the lights in the sky, but sometimes the deepest puzzles are found much closer to home, in the precise trajectories of our own robotic explorers. Our seventh discovery is the Pioneer anomaly, a tiny deviation in the path of two spacecraft that for decades hinted at a crack in the foundation of physics itself. In the early 1970s, NASA launched Pioneer 10 and Pioneer 11 on grand tours of the outer solar system. After their historic encounters with Jupiter and Saturn, they continued on, becoming the first human-made objects destined to drift forever among the stars. As they sailed into the deep, dark expanse beyond Pluto, scientists tracking their radio signals noticed something was off. The spacecraft were not quite where they should have been. An incredibly subtle but persistent force was acting upon them, a tiny but constant deceleration tugging them back toward the sun. This minuscule pull was equivalent to just 10 billionths of the gravity we feel on Earth's surface, but over millions of miles it added up to a detectable discrepancy. For nearly 30 years, this anomaly haunted physicists and engineers. It was as if the pioneers were driving with a faint, constant pressure on the brakes, a pressure that the equations of gravity and motion could not account for. The implications were staggering. Could this be evidence of a flaw in Einstein's theory of general relativity? Was some unknown form of matter or energy in the outer solar system exerting a drag? Perhaps it was a sign of new physics, a modification to the laws of gravity that would only reveal itself in the vast, weak field emptiness between the stars. Theories flourished, some suggesting the influence of dark matter, others proposing long-range modifications to the inverse square law of gravity. The Pioneer anomaly became a classic scientific detective story, a whisper of something wrong in the data that promised a revolution. The painstaking search for an answer was a masterpiece of forensic engineering. Teams of researchers dove into decades-old design documents, reconstructing every possible source of influence on the spacecraft. They modeled the faint push of the solar wind, the gravitational tug of distant objects, even the pressure from the spacecraft's own radio signals. For years, no conventional explanation fit. Then, through relentless effort, the culprit was finally found, not in the heavens but in the spacecraft themselves. The answer was heat. The Pioneers were powered by radioactive thermoelectric generators, which produced electricity from the decay of plutonium. This process also generated a substantial amount of waste heat. That heat radiated away from the spacecraft in all directions. Crucially, however, the Pioneers' large dish antennas acted as shields, reflecting more heat from their backsides than from their fronts. This created a tiny but exactly measurable imbalance. The photons of infrared light carrying that heat away also carried momentum, and the slight difference in radiation pressure from the front and back acted as a constant, gentle brake, pushing the spacecraft back toward the Sun. When this thermal recoil force was finally modeled with exquisite precision, the anomaly vanished. The pioneers were right where physics said they should be. The resolution of the Pioneer anomaly is a profound lesson in scientific humility. It was a ghost in the machine, a whisper of new physics that turned out to be the faint breath of our own technology. Yet its legacy endures, a decades-long reminder of how the universe can tease us with mysteries that lie not in distant galaxies, but in the meticulous details of our own backyard. It proves that sometimes the most logical defiance comes from forgetting to account for the gentle warmth of a machine's own heart. The gentle warmth of a spacecraft's heart is one thing, but the cosmos also produces bursts of raw, screaming energy that arrive without warning. Cosmic Discovery 8 brings us to the fast radio burst, an event so brief and powerful it redefines the word flash. These are not gentle pulses or steady signals. A fast radio burst is a blast of radio waves that travels across billions of light-years of space, compresses more energy than our Sun releases in 80 years, and then vanishes all within a few thousandths of a second. Their discovery was almost an accident. In 2007, an astronomer named Duncan Lorimer was sifting through old data from the Parkes Radio Telescope in Australia, searching for new pulsars. Buried in the recordings from 2001 was a spike of radio energy so intense it saturated the telescope's detectors. It was a single 5-millisecond blast that had arrived from a source far beyond our galaxy. For years, it was considered a possible fluke, a one-off glitch, but then another was found and another. Today, we have catalogued hundreds of these enigmatic bursts, each one a cosmic shout in the dark. The sheer power involved is the first layer of the mystery. To produce such a brilliant, short-lived flash across such vast distances, the source must be unimaginably violent. Early theories pointed to the most catastrophic events we knew, the final death cries of massive stars collapsing into black holes, or the mergers of incredibly dense objects like neutron stars. These are one-time, universe-shattering explosions, and they fit the profile of a single, never-to-be-repeated burst. But the universe, as always, had a surprise in store. In 2016, astronomers found a fast radio burst that did the impossible. It repeated, not just once, but again and again, in an irregular, unpredictable pattern. This discovery shattered the cataclysmic model. You cannot have a star die in a titanic explosion and then have it die again next week. The repeating bursts pointed to a source that could survive its own outburst, something that could produce these monstrous energies repeatedly. The leading candidate now is a type of neutron star with a magnetic field so strong it could erase a credit card from halfway to the moon, a magnetar. Under immense stress, a magnetar's crust might crack, releasing a starquake that unleashes a firestorm of radio waves. This could, in theory, happen more than once. Yet, even this compelling explanation faces challenges. Some of the repeating bursts show patterns that are bizarrely complex, with windows of activity followed by long periods of silence, and some bursts are far more energetic than any magnetar flare we have seen in our own galaxy. This lingering strangeness keeps other, far more speculative ideas on the table. Could these be the signatures of advanced technology? Perhaps the power beams of interstellar light sails, or the leakage from incomprehensibly large transmitters. While scientists heavily favor natural origins, the sheer extremity of fast radio bursts forces us to consider every possibility. They are the universe's most powerful and most cryptic Morse code, dots of energy fired across the dark. Each one that arrives is a message from a distant, violent event. But the message itself, the reason for the scream, remains locked in the briefest flash of static. While fast radio bursts are fleeting screams across the cosmos, our next discovery is a permanent, frozen whisper from the very beginning of everything. Etched into the oldest light we can see is a blemish so vast and so cold it should not exist. This is the cosmic microwave background cold spot, a chilling anomaly in the afterglow of the Big Bang itself. To understand its significance, you must first picture the cosmic microwave background. This is the remnant heat from the birth of the universe, a nearly uniform glow of microwave radiation that fills every direction of space. It is the ultimate baby picture of the cosmos, taken when it was just 380,000 years old. For the most part, this background is incredibly smooth, with only tiny, random variations in temperature, like the gentle texture on the surface of an orange. These variations were the seeds from which all galaxies and clusters would eventually grow. But in the constellation of Eridanus, there is a region that breaks all the rules. It is a circular patch of sky about 1 billion light-years across that is significantly colder than its surroundings. We are not talking about a slight chill. This spot is about 70 microkelvins colder than the average temperature of the cosmic microwave background, a massive deviation in a sea of remarkable uniformity. When scientists first identified it, they assumed it was a statistical fluke, a trick of the data. But as more sensitive satellites mapped the sky, the cold spot remained stubborn and real. Its existence presents a profound puzzle, because the standard model of cosmology has a very hard time explaining how such a large, coherent, and cold feature could have formed naturally in the infant universe. One leading and utterly mind-bending explanation is that the cold spot is a bruise. It could be the imprint of a collision between our universe and another bubble universe in a vast multiverse. According to some theories of eternal inflation, our universe is just one bubble in a frothing, infinite sea of other bubble universes, each with its own distinct physics. If, during the universe's earliest, most violent moments, our bubble brushed against another, the energy of that collision could have left a scar on the fabric of space-time, a region where energy was drained away, creating a cold spot in the cosmic background radiation. This idea is as revolutionary as it is untestable with our current technology, pointing to a reality far grander and more bizarre than we ever imagined. The other, more conventional explanation is that the cold spot is not a feature of the ancient radiation at all, but a modern illusion. It could be a shadow cast by a giant supervoid, an enormous region of space that is mostly empty, lying between us and the cosmic microwave background. As light from the ancient afterglow travels through such a void, it must climb out of a gravitational well, losing energy and shifting to longer, colder wavelengths in a process known as the integrated Sachs-Wolf effect. This would make the region appear colder to our telescopes. The problem is scale. To create a shadow this large and this cold, the void would need to be unimaginably vast and profoundly empty, far exceeding any other void we have observed, including the one in Boötes. Astronomers have searched for such a supervoid in the direction of the cold spot. They have found evidence of a large underdense region, but its size and emptiness do not seem sufficient to explain the extreme temperature drop. The math once again falls short, so we are left with two deeply unsatisfying possibilities. Either the cold spot is evidence for a collision with another universe, a concept that stretches the definition of science, or it requires a void so preposterously large it defies our understanding of cosmic structure. Both roads lead to a radical conclusion that our standard model of the universe is missing a crucial piece. The cold spot is a fossil, a cosmic birthmark that tells a story we are only beginning to decipher. Is it the signature of a sibling universe, or simply a shadow from an emptiness we cannot fully comprehend? Either way, it is a cold, hard reminder that our universe's first light still holds secrets we have yet to warm up to. From the cold, ancient whisper of the cosmic background, we jump to a modern encounter with a silent visitor from beyond. In October 2017, astronomers at the Pan-STARRS telescope in Hawaii spotted a faint point of light moving against the stars. Its trajectory was unlike anything seen before. It was not orbiting the sun, it was passing through, and it was moving far too fast to be bound by our star's gravity. This was the first confirmed visitor from another star system, an interstellar object. They named it Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. Its arrival was a historic moment, but its behavior quickly turned celebration into profound bewilderment. The first puzzle was its shape. As Oumuamua tumbled through the solar system, its brightness changed dramatically by a factor of 10 every few hours. This extreme variation meant only one thing: the object was not round. To reflect light in such a pattern, it had to be highly elongated, shaped like a cigar or a pancake. Estimates suggested it was up to 10 times longer than it was wide, a shape unlike any natural asteroid or comet we have seen in our own system. This was strange, but the real defiance of logic came from its motion. After Oumuamua whipped around the sun, astronomers tracked its path with extreme precision. They found it was not just coasting under the influence of gravity alone. Something was giving it an extra push, a tiny but consistent acceleration away from the sun. This is a common feature of comets, as sunlight vaporizes their icy surfaces, creating jets of gas that act like weak rocket engines. The problem was, Oumuamua showed no signs of being a comet. Our most powerful telescopes saw no coma, the fuzzy cloud of gas and dust that surrounds an active comet's nucleus. They detected no outgassing, no tail whatsoever. It appeared as a dead, rocky asteroid, yet it was accelerating like a comet. Scientists scrambled for explanations. Perhaps it was a very old comet with its volatile ices hidden beneath a thick, insulating crust. When sunlight warmed it, deeply buried ice could have turned to gas and escaped through narrow jets, providing thrust without creating a visible cloud of dust. This was possible, but it required a very specific and unusual composition. The absence of any visible dust was particularly troubling, as even the faintest comet activity should have left some trace we could detect. The mystery of its acceleration, combined with its bizarre shape, opened the door to more speculative ideas. The most famous, proposed by Harvard astronomer Avi Loeb, was that Oumuamua could be a piece of alien technology, specifically a light sail. A light sail is a thin, reflective sheet that uses the pressure of sunlight for propulsion, much like a boat's sail uses wind. A broken fragment of such a sail tumbling through space could explain the strange acceleration, the unusual shape, and its high reflectivity. It would be a piece of cosmic debris from a civilization we will never know. The scientific community largely favors a natural origin, with ongoing research suggesting that Oumuamua could be a fragment of a Pluto-like planet from another star system, a chunk of solid nitrogen ice that eroded in a way that produced the observed thrust. Yet, even this natural explanation is exotic, requiring a type of object we have never directly seen. Oumuamua is now far beyond the reach of our telescopes, speeding back into the interstellar dark. It left behind no definitive answers, only a trail of questions. Was it a strangely shaped comet that defied our expectations, a fragment of a distant, frozen world, or a relic of something beyond nature? Its true legacy is the proof it delivered, not of aliens, but of our own cosmic ignorance. The galaxy is full of travelers, and we have only just begun to notice them. The next one could already be on its way. The silent departure of Oumuamua left us questioning the nature of cosmic travelers, but sometimes the greatest puzzles are not the visitors but the residents. Our next discovery is a galaxy that should not be, a cosmic rebel that defies the very rules we thought governed all galaxies. It is called NGC 1052DF2, and it appears to be missing the universe's most essential ingredient, dark matter. For decades, the standard model of cosmology has rested on a foundational pillar. Dark matter, that invisible, mysterious substance, is the gravitational glue that holds galaxies together. It forms vast, diffuse halos that cradle the visible stars, providing the extra gravity needed to keep fast-moving stars from flying off into the void, and to explain how galaxies formed so quickly after the Big Bang. Every galaxy we have studied, from majestic spirals to tiny dwarfs, has been dominated by this dark scaffolding, until we found this one. NGC 1052DF2 is a ghostly, diffuse galaxy, a wispy collection of stars so spread out you can practically see right through it. When astronomers measured the motions of its star clusters, they expected to see the telltale signs of a massive dark matter halo, the high speeds that betray unseen gravity. Instead, they found something astonishing. The clusters were moving slowly, lazily, exactly as they would if the only gravity present came from the visible stars themselves. The math was clear. This galaxy contained at most a tiny fraction of the dark matter every other galaxy possesses. Its existence is a direct challenge, a cosmic contradiction. If dark matter is essential for galaxy formation, how did this one come together without it? One immediate line of inquiry questioned the galaxy's distance. If we had miscalculated how far away it was, we could also be wrong about its mass and the speeds of its stars. Some astronomers argued it might be much closer, making it a smaller, more ordinary object. However, precise follow-up observations with the Hubble Space Telescope have largely confirmed the original distance, placing it about 65 million light-years away, solidifying its strange properties. This only deepens the mystery. How do you build such a thing? One compelling theory is one of galactic violence. Perhaps NGC 1052DF2 is the shredded remnant of a catastrophic encounter. Imagine two galaxies colliding, their dark matter halos passing through each other like ghosts, while their visible gas and stars get pulled and stretched by tidal forces. In this chaotic process, a clump of stars could have been ripped clear of its dark matter anchor, left to drift as a dark matter-free island. This would make it a celestial orphan, a piece of a galaxy that lost its hidden skeleton. Yet, even this dramatic story has problems. The galaxy looks remarkably tranquil and intact, not like a violently torn-apart wreck. Its stars are old, suggesting a quiet history. The debate rages on, with some scientists proposing it formed in a rare, ultra-dense filament of gas in the early universe, where normal matter was packed tightly enough to coalesce under its own gravity without needing a dark matter crutch. Others wonder if its dark matter was somehow stripped away by a nearby massive galaxy, though there is no obvious culprit. The discovery of NGC 1052DF2 and a handful of other similar oddballs found since forces a profound reevaluation. It proves that dark matter and visible stars are not inseparably tied. They can, under circumstances we do not yet fully understand, come apart. This galaxy is not just an anomaly, it is a control experiment. By studying a galaxy that lacks dark matter, we can better understand what dark matter actually does in all the others. It turns a theoretical framework into a comparative study, offering a glimpse of what the universe looks like when the hidden hand simply lets go. That galaxy without dark matter shows us how the rules can be rewritten, but in our own solar system, a different kind of rule is being broken, a rule of chaos. Above the North Pole of Saturn, a storm is raging that has not changed its mind in over 40 years. It is not a swirling vortex like Jupiter's Great Red Spot. This is a hurricane over 20,000 miles wide with a shape so precise it looks machined. It is a perfect hexagon. Imagine a six-sided figure, each side longer than the entire Earth, etched into the clouds of a gas giant. This is not a fleeting arrangement. The Voyager probes first glimpsed it in the early 1980s. When the Cassini spacecraft arrived over 2 decades later, the hexagon was still there, unwavering, a permanent geometric tattoo on Saturn's atmosphere. The sheer longevity is the first defiance of logic. Planetary weather is the definition of turbulence, a chaotic system where small changes amplify into massive storms that eventually dissipate. Yet here is a structure with razor-sharp corners, maintaining its exact shape through seasons that last for years, through countless smaller storms that should have eroded its edges into a blur. How does a perfect polygon persist in a fluid, churning environment? The secret lies in what we cannot see directly, in the complex dance of fluids deep below the cloud tops. Scientists believe the hexagon is a giant, standing wave pattern in Saturn's fast-moving jet stream. It is akin to a harmonic that forms when you vibrate a plate of liquid, creating stable, geometric patterns in the ripples. On Saturn, the plate is the entire northern hemisphere, and the vibration is the planet's own rotation and the turbulent flow of its atmosphere. The jet stream acts like a winding river, and something is causing that river to oscillate in precisely 6 peaks and 6 troughs, pinning the pattern in place relative to the planet's spin. To understand this, researchers have turned to laboratory tanks, spinning fluids of different viscosities to simulate planetary atmospheres. In these experiments, they can indeed create polygonal shapes, including squares and hexagons at the center of a spinning cylinder. The key factors are the speed of rotation and the difference in wind speeds between the jet stream and the surrounding atmosphere. When conditions are just right, the fluid naturally settles into a stable, geometric standing wave. Saturn, with its rapid 10-hour rotation and its layered atmosphere, seems to have hit upon that perfect recipe for a 6-sided wave, but the mystery deepens when we consider the scale. Laboratory models are inches across. Saturn's hexagon is wide enough to fit 4 Earths side by side. Translating those small-scale fluid dynamics to a planetary giant involves complexities we are still unraveling, like the role of Saturn's deep internal heat or the varying depths of its weather layers. The hexagon is more than a curiosity, it is a natural laboratory. Its enduring perfection gives us a unique window into the hidden forces shaping gas giants, offering clues about the wind speeds, densities, and rotational dynamics far below the visible clouds. It proves that even in the realm of chaos, under the right conditions, order can emerge and lock itself into place for generations. It is a cosmic lesson in stability, written in clouds and wind, a 6-sided reminder that the universe often hides its most elegant answers in plain sight. Saturn's perfect geometry is a marvel of atmospheric order, but from the depths of space come projectiles of pure chaos, particles moving with a fury that shreds the laws of physics as we know them. Cosmic Discovery 13 is the mystery of ultra-high-energy cosmic rays. These are not rays of light, they are atomic nuclei, the hearts of atoms like iron or oxygen, stripped of their electrons and hurled across the universe at velocities so close to the speed of light they carry energies beyond comprehension. A single one of these subatomic bullets packs the punch of a professionally thrown baseball, condensed into a particle smaller than an atom. Its energy is over 100 million times greater than anything achieved in our most powerful human-made accelerator, the Large Hadron Collider. Detecting these ghosts is a feat of indirect observation. When such a particle, traveling at nearly the speed of light, slams into the top of Earth's atmosphere, it triggers an apocalyptic cascade. It collides with an air molecule, shattering it and creating a shower of secondary particles, which then collide and create more, resulting in a downward avalanche of billions of particles spreading over miles. Scientists detect this shower not by catching the original particle, which is long gone, but by capturing the faint ultraviolet glow it produces in the air or by using arrays of detectors on the ground to map the fallout. The existence of these particles is the first layer of the mystery. The second and far more baffling layer is how they got here at all. According to our understanding of physics, they should not be able to travel vast cosmic distances. The universe is not empty, it is filled with the cosmic microwave background radiation, that faint afterglow of the Big Bang. For an ultra-high-energy proton or atomic nucleus, this sea of photons is like running through a relentless hail of bullets. Each collision with a background photon saps a little of the particle's energy, a process physicists call the Greisen-Zatsepin-Kuzmin or GZK cutoff. Over distances greater than about 150 million light-years, this interaction should drain these cosmic rays of their ultra-high energy. They should arrive at Earth completely depleted, like a marathon runner collapsing after a race through a storm. Yet they do arrive. This means their sources must be relatively close to us, cosmically speaking, within our local supercluster of galaxies. They are coming from our cosmic backyard, and something within it is capable of launching atomic nuclei to energies that dwarf anything in nature we understand. So what cosmic cannon could possibly fire them? The hunt for the source is a monumental detective story, requiring global networks of detectors to triangulate the direction of the most powerful events. The prime suspects are the most violent engines in the universe. At the top of the list are active galactic nuclei, the frenzied cores of galaxies where supermassive black holes are actively devouring matter. As material spirals into the black hole's maw, it heats to incredible temperatures and can be funneled by magnetic fields into jets of plasma that shoot out at nearly light speed for millions of light years. These jets are perfect candidate accelerators, cosmic versions of our particle colliders, but on a scale we can barely imagine. Other suspects include the cataclysmic deaths of massive stars as hypernova, or the mergers of neutron stars, events that unleash gravitational tsunamis and electromagnetic firestorms. Yet, even with these fantastic candidates, the plot thickens. When scientists trace the paths of the highest energy cosmic rays back into the sky, they often do not point to any obvious, brilliant source like a known active galaxy. They seem to come from empty space or from directions where multiple potential sources blur the picture. This suggests our maps of the violent universe are still incomplete, or that these particles are being bent and twisted by the magnetic fields that weave between galaxies, obscuring their true origins. They are cosmic fugitives, their paths scrambled, leaving us with the evidence of a crime but no clear address for the perpetrator. Each one that strikes our atmosphere is a messenger from a celestial powerhouse, carrying a coded letter about the most extreme physics in the cosmos. But the letter is smudged, the return address illegible. The mystery of ultra-high-energy cosmic rays is not just about what they are, but about the unimaginable violence happening just down the cosmic street. Violence so great it can turn an atom into a cannonball and fire it across the dark directly at us. That cosmic cannon fire is a testament to invisible violence, but some of the universe's most stunning acts of defiance are not hidden. They are on display in breathtaking color. Drifting in the constellation Monoceros, the unicorn, is a dying star that has chosen a spectacularly geometric way to leave this world. Known as the Red Rectangle Nebula, it is a masterpiece of cosmic symmetry, a glowing hourglass of crimson gas and dust with a stark, X-shaped structure at its heart. This is not the chaotic, billowing cloud of a typical planetary nebula. It looks engineered, as if drawn with a ruler and compass by a celestial architect. The story begins with a binary star system at its core, two aging suns locked in a close, mutual orbit. One of these stars has exhausted its nuclear fuel and is in its death throes, shedding its outer layers into space. In a lone star, this process often creates a roughly spherical shell, a bubble of glowing gas expanding in all directions. But here, the presence of the companion star changes everything. The two stars are surrounded by an incredibly dense, thick disk of dust and gas, a donut-shaped torus that constricts the dying star's outflow. Imagine trying to inflate a balloon inside a narrow tube. The gas cannot expand evenly outward. Instead, it is forced to escape above and below the disk, rushing out in two opposing cones. As these twin jets of gas shoot away, they are sculpted further by the orbital motion of the binary stars themselves. The star's dance causes the jets to precess, to wobble like a spinning top, tracing out a conical pattern over time. The result is not a smooth cone, but a series of concentric hollow shells, like a stack of ice cream cones placed tip to tip. From our vantage point, looking nearly edge-on at this dense central disk, we see the rims of these nested cones. They create the illusion of the glowing red rectangle, with the dark dust lane of the disk bisecting it, and the intersecting lines of the cone walls forming the dramatic X. The vibrant red color comes from a specific type of emission, as ultraviolet light from the hot stellar core causes hydrocarbon molecules in the outflow to fluoresce, a process similar to the glow of a neon sign. This nebula is more than just a pretty picture, it is a cosmic clock. The spacing of the concentric rims corresponds to the precession period of the binary system, allowing astronomers to measure the timing of the stellar dance that created it. It is a fossil record of the system's final centuries, etched in light and gas. The red rectangle challenges our expectations of stellar death. It proves that the chaos of a star's end can, under the right conditions, produce extraordinary order. It is a reminder that the universe is not just a place of random explosions, but also of precise natural sculpting, where gravity, rotation, and light collaborate to create artwork on a scale that spans trillions of miles. We are witnessing a temporary monument, a structure that will eventually dissipate into the interstellar medium, leaving behind only the fading embers of its white dwarf core. For now, it hangs in the void, a perfect geometric testament to the beautiful, intricate physics of a double star's final bow. That geometric perfection is a fleeting wonder, but some cosmic structures are built to last, woven from a fabric we cannot see. Drifting in the faint constellation Coma Berenices is a galaxy so ghostly, it was only discovered in 2015. Its name is Dragonfly 44, and it is a place where the universe's hidden skeleton has stepped out of the shadows to become almost the entire body. From a distance, it looks like a smudge, a wispy collection of stars so diffuse that it was missed by every major sky survey for decades. It took a specially designed telescope array, the Dragonfly telephoto array, which uses commercial camera lenses to excel at spotting extremely faint, spread-out structures to finally reveal it. What the Dragonfly saw was a galaxy the size of our Milky Way, but one that emits less than 1% of the light. It is a cosmic phantom, a gauzy veil of stars stretched across an immense volume of space. The true nature of Dragonfly 44 only became clear when astronomers turned their spectrographs toward it, measuring the velocities of its star clusters. The speed at which objects orbit in a galaxy reveals the mass holding them in place, like swinging a ball on a string faster requires a stronger grip. The results were staggering. The few visible stars in Dragonfly 44 were moving at tremendous speeds, whirling around so fast that the gravity from their own combined mass was utterly insufficient to hold them. They should have been flung into the void long ago. The math pointed to only one conclusion: this galaxy possesses a colossal amount of mass that is completely invisible. Calculations show that a staggering 99.99% of Dragonfly 44 is made of dark matter. For every single atom of visible, glowing star stuff, there are nearly 10,000 units of this mysterious, unseen substance. It is the most extreme dark matter-dominated galaxy ever found, a place where the shadow universe has built a cathedral and left only a handful of candles burning inside. This discovery turns our understanding of galaxy formation on its head. We thought dark matter halos were necessary to gather gas and birth stars, but we assumed there was a rough balance, a partnership between the dark and the light. Dragonfly 44 shows that partnership can be almost completely one-sided. It forces us to ask how such a thing could even exist. Did it form in an unusually dense knot of pure dark matter that gathered only a tiny sprinkling of gas? Or was it once a more normal galaxy that had almost all of its gas and stars stripped away by a violent encounter, leaving behind the indestructible dark matter halo like a cosmic husk. Its existence in the crowded Coma galaxy cluster, a region known for gravitational harassment between galaxies, supports this latter violent story. It may be the ghost of a galaxy, the durable dark matter framework that remains after a celestial body has been picked almost clean. Yet, its very survival as a coherent object is a vital clue. It proves that dark matter can clump and hold together in these massive, galaxy-sized halos independently of the stars. Dragonfly 44 is not an anomaly, it is a pure sample. By studying this ghost, we are studying dark matter in its most undiluted form, a laboratory for understanding how this invisible scaffolding dictates the architecture of the cosmos without the distraction of bright lights. It is a silent, dark monument, proving that what we see in the night sky is merely the decorative trim on a universe built from shadows. From a galaxy built almost entirely from shadows, we return to the light of a single, small star and the 7 worlds that circle it. The TRAPPIST-1 system captured global imagination, a red dwarf star just 40 light-years away orbited by a family of 7 rocky planets, 3 of which sit snugly within the habitable zone where liquid water could exist. Here, it seemed, was our best chance to find life beyond Earth. But as astronomers studied this compact system more closely, they encountered a profound and puzzling silence. Red dwarf stars like TRAPPIST-1 are notorious for their violent tempers. They are known to erupt in frequent, powerful flares, blasting their planets with torrents of X-rays and ultraviolet radiation. These stellar tantrums can strip away atmospheres, boil off oceans, and sterilize surfaces. Given the planets in the TRAPPIST-1 system orbit incredibly close to their star, with years that last only a few Earth days, logic dictated they should be constantly bathed in this hostile radiation, their chances for habitability scorched away. Yet, when scientists pointed space telescopes like Hubble and Spitzer to monitor TRAPPIST-1 for signs of this expected fury, they found something startling. The star was quiet, remarkably, almost eerily quiet. It showed very little flare activity. This calm demeanor defies the established profile for a star of its type and age. It is as if we discovered a notorious, unpredictable volcano that has, against all odds, entered a period of profound and lasting peace just as we arrived to study it. This quietness poses a fascinating double-edged mystery. On one hand, it is a gift for the potential survival of those worlds. A calm star means atmospheres might have had a chance to form and persist. It means conditions on the surface could be less hellish. The possibility for habitability against all prior odds suddenly seems more plausible. But on the other hand, the silence raises a deeper, more fundamental question. Why is TRAPPIST-1 so well behaved? Is this star uniquely stable, or have we simply caught it in an unusually long period of calm? Some theories suggest its advanced age for a red dwarf may have mellowed its magnetic activity. Others propose that the planets themselves, through complex magnetic interactions, could be exerting a calming influence on their host star, a cosmic feedback loop where the children steady the parent. There is also the haunting possibility that we are witnessing a system after a great filtering event. Perhaps the star was once violently active in its youth, and that early fury did exactly what we feared. It stripped the planets bare, leaving behind barren, airless rocks. Their current orbits within a quiet stellar environment would then be a tragic irony, a habitable zone rendered permanently uninhabitable by ancient violence. The truth about TRAPPIST-1 remains locked in that quiet light. Future observations with the James Webb Space Telescope aim to peer directly at the planets, searching for the chemical signatures of atmospheres. Finding thick, complex atmospheres would be a revelation, suggesting not only that worlds can survive around red dwarfs, but that our galaxy could be filled with such opportunities. Finding nothing or only the thin traces of long-dead air would tell a different but equally important story about the harsh realities of cosmic real estate. This famous system, with its 7 tantalizing worlds, now presents us with a cosmic riddle of stillness. Is it quiet a promise, or is it the silence of a graveyard? The answer will redefine our search for life, teaching us whether the most common stars in the galaxy are harbors for new Earths or sentinels of perpetual solitude. The quiet contemplation of distant stars is shattered by the sheer violence of cosmic eviction. A supermassive black hole, an anchor weighing millions of suns, has been caught in the act of fleeing its home galaxy. It is not drifting quietly, it is screaming across the void at phenomenal speed, and behind it, it is painting a trail of fire. This is no ordinary escape, it is a cosmic crime scene with a brilliant, contradictory clue. The black hole, first detected as a bright, point-like quasar, was not sitting in the heart of a galaxy where such monsters belong. Instead, it was streaking through intergalactic space, and stretching behind it for over 200,000 light-years was a narrow, brilliant bridge of young, blue stars. This is the baffling evidence, a contrail of stellar birth following an engine of destruction. The logic here is completely inverted. Black holes are famous for consuming light and matter, for tearing stars apart. They are not known for creating them, yet this rogue behemoth is doing exactly that, forging new suns in its chaotic wake. How is this possible? The answer lies in the physics of its violent exit. Astronomers believe this black hole was once part of a triple system at the center of a merging galaxy. When 3 supermassive black holes dance too close together, their gravitational interactions become a chaotic game of cosmic billiards. The lightest of the 3 can be slingshotted out at incredible speed, a process known as a gravitational slingshot. In this case, the ejected black hole did not leave empty-handed. As it was violently propelled from the galactic core, it dragged along with it a vast reservoir of gas from its former accretion disk and the surrounding region. This dense, cold gas was compressed and shocked in the black hole's turbulent wake. Think of a speedboat racing across a calm lake, churning up water and creating a foamy, turbulent trail behind it. The black hole is that boat, and the gas is the lake. The immense compression and shock waves in that trailing gas triggered a frenzy of star formation, lighting up its path with stellar nurseries. So we are witnessing a dual defiance of expectations, a supermassive black hole where it should not be, performing an act it should not be capable of. Its very existence confirms the most violent of galactic interactions, a rare 3-body breakup on a scale that bends the mind. The trail of young stars is not just a beautiful accident, it is a forensic marker, a glowing breadcrumb trail that maps the black hole's frantic journey out of its galaxy and into the eternal dark. It proves that even the universe's most destructive forces can, under the right conditions of chaos, become unwilling midwives to creation. Where this runaway giant is headed, and whether its star-forming journey will eventually cease, remains one of the most dynamic and violent mysteries on the cosmic road. That rogue black hole forging stars in its wake shows creation born from destruction, but some cosmic evidence points to a form of matter that defies the very definition of what a particle should be. Deep within the data from our most powerful particle detectors and cosmic ray observatories, there are faint whispers of something that should not exist according to our standard model of physics. This theoretical ghost is known as unparticle matter, and it represents a possibility so strange it feels like science fiction. To grasp what an unparticle is, you must first understand what a normal particle is. In our universe, everything is made of particles like electrons and quarks. These particles have specific fixed masses and obey well-defined rules. They exist in discrete states. You can have 1 electron or 2, but never 1.5. Their behavior is predictable within the frameworks of quantum mechanics. Unparticles, as proposed by physicist Howard Georgi, would shatter this tidy picture. They would not have a specific mass at all. Instead, they would possess something called scale invariance. Imagine a cloud in the sky. You cannot point to a single piece of the cloud and call it a discrete, countable object. The cloud is a continuous flowing entity without a fixed form or a smallest unit. An unparticled cloud would behave like that, as a continuous, fractional substance rather than a collection of individual bits. It would not be made of particles in the traditional sense, hence the name. The theoretical pathway to such a substance involves a hidden sector of the universe, a realm with its own forces and particles that interact with our familiar world only through gravity or incredibly weak forces. At very high energies, this hidden sector could contain particles, but as the universe cooled, those particles could undergo a transformation, melting into this scale-invariant, unparticled stuff. How would we ever detect such a phantom? The clues might lie in the things we cannot explain. Some measurements of cosmic rays, those high-energy messengers from deep space, show slight anomalies in how they interact with Earth's atmosphere. Certain rare particle collisions in giant underground labs produce energy signatures that are a tiny bit off from theoretical predictions. These discrepancies are minuscule, buried in statistical noise, but they are persistent. Could unparticles be the cause? The idea is that this ethereal substance could mediate new, ultra-weak forces or subtly alter the outcomes of particle decays and cosmic ray showers in ways that our current models do not account for. The evidence remains speculative, a tantalizing hint at the edge of our instrument's sensitivity. Proving the existence of unparticles would be a revolution on par with the discovery of quantum mechanics itself. It would mean that at certain scales, the universe is not granular, but smooth and continuous in a way we have never imagined. Matter would not always come in countable lumps. It could exist as a fractional, cloud-like essence. For now, unparticles remain a beautiful, haunting idea, a mathematical possibility waiting for a definitive signal from the cosmos. They challenge the foundational assumption that everything is built from distinct, Lego-like blocks, suggesting instead that the building materials of reality might, in some hidden corner, be more like a mysterious, intangible fog. The phantom idea of unparticled matter suggests a reality beyond particles, but we have already caught one type of cosmic ghost, and it led us straight to a monster. In 2017, an alert shot through the global astronomical community. A single, nearly massless particle, a high-energy neutrino, had struck the Ice Cube Neutrino Observatory deep in the Antarctic ice. This in itself was not unusual. Ice Cube detects neutrinos all the time. But this one was special. It carried an astronomical amount of energy, and for the first time ever, its arrival direction could be traced back to a specific, brilliant source in the distant cosmos. That source was a blazar, a galaxy with a supermassive black hole at its core firing a jet of radiation and particles directly at Earth. This blazar, with the catalog number TXS0506+056, was caught in the act of firing a neutrino bullet at us. This event, Cosmic Discovery 19, marked the dawn of a new era, multi-messenger astronomy, where we do not just see the universe, we feel it. Neutrinos are the ultimate ghosts. Trillions pass through your body every second, leaving no trace. They interact so weakly with matter that they can travel straight through planets and stars without slowing down. This makes them incredible messengers, carrying information directly from the heart of the most violent events. But it also makes them nearly impossible to catch and even harder to trace. Pinpointing where a neutrino comes from is like trying to find the source of a single, specific raindrop in a hurricane after it has already hit the ground. The Ice Cube detector achieves this almost impossible task by using a cubic kilometer of pristine Antarctic ice as a trap. When a rare, high-energy neutrino does interact with an atom in the ice, it produces a faint flash of blue light called Cherenkov radiation. By mapping the precise pattern and timing of this light with thousands of embedded sensors, scientists can reconstruct the neutrino's energy and, crucially, its incoming direction. The neutrino from blazar TXS0506+056 was a direct hit. When the Ice Cube coordinates were sent out, telescopes across the globe and in space swiveled to look. There, blazing in gamma rays, X-rays, and visible light, was the blazar over 4 billion light-years away. The significance of this connection cannot be overstated. For decades, we knew that cosmic accelerators like blazar jets must produce high-energy particles, protons, and atomic nuclei. But these charged particles get bent and scrambled by magnetic fields on their long journey, obscuring their origins. Neutrinos, being neutral ghosts, travel in straight lines. They are the smoking gun, the direct evidence that this specific blazar is a cosmic particle accelerator of unimaginable power. The detection tells us that within those relativistic jets, protons are being accelerated to near light speed and then colliding with photons or other matter, producing not just light, but these elusive neutrinos as a byproduct. This solves a century-old mystery, identifying at least one source of the ultra-high-energy cosmic rays that bombard our atmosphere, but it also deepens the puzzle. The amount of energy required to produce such a high-energy neutrino is staggering, pushing the limits of what we think even these monstrous black hole jets are capable of. It forces us to refine our models of the chaotic, magnetized maelstrom at the heart of an active galaxy. Finding this one ghost particle was a triumph of patience and technology, a message in a bottle that traveled across half the universe to tell us exactly where it was bottled. It proves that to truly understand the cosmos, we must learn to listen not only with our eyes, but with every sense we can possibly build, catching the whispers of ghosts to find the roar of the engines that made them. Ghostly particles point to the engines of creation, but the very architecture of our home galaxy presents a puzzle of its own, a choreography that should not exist. Around our Milky Way and around our neighboring giant Andromeda dance dozens of small satellite galaxies. These are the cosmic equivalent of moons, dwarf galaxies held in the gravitational grip of their larger hosts. According to our most successful models of how the universe builds structure, these satellites should arrive from all directions. They should swarm their host like bees around a hive, orbiting in a messy, thick, three-dimensional cloud with orbits tilted every which way. This is what the cold dark matter model predicts, a random distribution born from billions of years of chaotic mergers and accretions. The reality, however, is a stunning defiance of this expectation. The satellites of the Milky Way are not randomly scattered. A great many of them, including the prominent large and small Magellanic Clouds, are aligned. They orbit within an astonishingly thin, pancake-like plane that slices through our galaxy. Even more perplexing, they are not just sharing a common plane. Many of them are moving in the same direction along that plane, like cars all driving the same way on a vast celestial roundabout. This coordinated rotation is not a fluke of our local neighborhood. The Andromeda Galaxy, over 2 million light-years away, exhibits the same strange feature. Its major satellites are also arranged in a thin, rotating plane. This synchronized dance presents a fundamental challenge. How can dozens of independent galaxies, each with its own complex history, end up orbiting in such a precise, aligned formation? It is as if you threw a handful of marbles into the air around a bowling ball, and they all decided to circle it in a neat, flat ring, all spinning the same way. The odds of this happening by chance under the standard model are astronomically low. One compelling, yet controversial, explanation involves the flow of cosmic gas. Perhaps these satellite galaxies did not form in isolation and then get captured. Instead, they might have been born together, condensing out of a single, vast river of cold gas that fell into the early Milky Way and Andromeda. As this gigantic filament of gas spiraled into the growing galaxy, it could have fragmented into many smaller clumps, all inheriting the same rotational direction and orbital plane, like droplets flung from a spinning wheel. This would make them a family, siblings born from the same event, explaining their coordinated motion. Another, more radical idea questions the very nature of dark matter. The standard cold dark matter model relies on particles that move slowly and clump easily. Some scientists propose that dark matter might be warm, meaning its particles were moving fast in the early universe. This warmth would suppress the formation of small structures, potentially leading to fewer, larger satellites that form along these primordial gas filaments, naturally creating aligned planes. Yet, even these explanations struggle with the longevity of these structures. The gravitational tug of the massive host galaxy and the satellites pulling on each other should have disrupted these delicate planes over billions of years. The fact that we see them today, intact and rotating, suggests they are either surprisingly stable or were formed much more recently than we think. This synchronized rotation is more than a curious alignment, it is a direct test of our cosmic origin story. Those faint smudges of light orbiting our galactic giants are not just decorative, they are witnesses, and their testimony contradicts the simplest version of how we believe galaxies gather their companions. Their coordinated dance is a silent rebuke, a hint that the early universe was woven with threads of structure far more coherent and influential than our simulations have yet been able to capture. The synchronized dance of satellite galaxies hints at a universe that built itself with startling speed, but the deepest look back in time has now revealed a cosmos in an impossible hurry. The James Webb Space Telescope, our most powerful window into the infant universe, has found galaxies that should not be. These are not the faint, chaotic blobs of primordial star formation astronomers expected to see in the universe's first few 100 million years. Instead, they are colossal, massive, and already serene, fully formed cosmic cities shining with the light of billions of suns. They are so mature and so enormous that their very existence defies every established timeline for how galaxies grow. It is like opening a family photo album and finding a picture of a fully grown adult labeled Age 1. The logic of cosmic evolution is cracking. For decades, our models painted a gradual picture. After the Big Bang, the universe was a dark, swirling soup of hydrogen and helium. Tiny fluctuations, seeds imprinted by quantum noise, slowly gathered more gas under the pull of dark matter. Over hundreds of millions of years, these clumps merged, collided, and began to spark with the first stars, chaotic and massive. Only after billions of years of this hierarchical buildup did majestic, structured spiral and elliptical galaxies like our Milky Way emerge. The James Webb Telescope was designed to see the very first chapters of this story, to witness those initial, fragile constructions. What it saw instead were finished skyscrapers on a landscape where we expected only foundations and scaffolding. Some of these galaxies are 10 times more massive than predictions allowed for that early epoch. Others show disks and structures of stunning order, suggesting a rapid, mysterious transition from chaos to calm that our physics cannot easily explain. The immediate question is a profound one: how did they get so big, so fast? The slow accretion of gas and the stately dance of mergers simply cannot account for such breakneck growth. It is as if the universe had a secret, faster recipe for building galaxies, one we have not yet discovered. One possibility is that the first stars formed with an unbelievable efficiency, converting nearly every available atom into stellar light with none of the wasteful feedback that slows star formation in later eras. Another, more radical idea points back to the invisible hand, dark matter. Perhaps the dark matter halos in the early universe were far denser and more concentrated than our simulations predict, creating deeper gravitational wells that sucked in ordinary matter at a ferocious rate. There is even a speculative notion that some of these impossible objects are not galaxies at all, but vast, glowing clouds lit up by the furious feasting of supermassive black holes, their light masquerading as starlight. Each explanation strains our current understanding, pushing the laws of physics and cosmology into uncomfortable new territory. The implications are staggering. If galaxies can mature this quickly, then the entire cosmic timeline might be compressed. Life in the universe could have had a much earlier start, with whole civilizations potentially rising and falling billions of years before our solar system even coalesced from stardust. The James Webb's discoveries are not just adding details to a known story, they are demanding that we rewrite the book. These impossible early galaxies are more than distant points of light. They are urgent messages from the dawn of time, telling us that our universe's childhood was far more dramatic, far more productive, and far more mysterious than we ever dreamed. While entire galaxies defy our timeline, a single point of light closer to home pulses with a rhythm that mimics life itself. In the constellation Aquila, a system known as JUBRIS 1915+105 sends out a powerful, repeating signal in X-rays that astronomers can only describe as a heartbeat. This is not a star's gentle throb, but the violent, ticking clock of a black hole feeding, a microquasar where matter is being torn apart in a frantic, rhythmic dance just milliseconds from the point of no return. The heartbeat is not a constant drumbeat. It is a quasi-periodic oscillation, a pulse that varies in both its rhythm and its intensity, sometimes speeding up, sometimes slowing down, but always maintaining a recognizable pattern over years of observation. To produce such a signal, we must look at the extreme physics of the accretion disk, the swirling, superheated maelstrom of gas spiraling into the black hole. As matter falls inward, it does not flow smoothly like water down a drain. It piles up, grows unstable, and then dumps onto the black hole in sudden, massive avalanches. The leading theory for this cosmic heartbeat involves a delicate and terrifying balance between two fundamental forces, heat and gravity. Imagine a city's water reservoir behind a dam. Pressure builds as water flows in until suddenly the dam bursts, releasing a catastrophic flood. Then the cycle begins again as the reservoir refills. At the edge of this black hole, the dam is the force of radiation pressure. As the inner part of the accretion disk fills with hot gas, the intense radiation it emits pushes outward, actually holding back the flow of new material. This creates a traffic jam of superheated plasma. The pressure and temperature build to a critical breaking point until the radiation can no longer hold back the tide. Gravity wins, the dam breaks, and a colossal torrent of matter surges over the event horizon in a burst of X-rays that we detect as one beat of the heart. Then the inner disk is emptied, the radiation pressure drops, and the cycle resets. What makes this heartbeat so baffling is its persistence and its complexity. It reveals that the process of accretion is not a simple, chaotic free-for-all. It can self-organize into a semi-regular cycle, a natural feedback loop of cosmic proportions. This challenges simpler models of accretion disks, which often predict smoother or more random emissions. Here, the black hole's feeding frenzy has a cadence, a signature of instability that we can measure and study. The variations in the heartbeat's tempo are clues, telling us about changes in the rate of matter flowing in from the companion star, or shifts in the magnetic field lines threading the chaotic disk. By listening to this X-ray rhythm, we are essentially taking the black hole's pulse, diagnosing the conditions in the most violent gravitational environment we can observe. It is a direct probe of physics where space-time is warped beyond recognition, showing us that even in the realm of ultimate darkness, there can be a strange, violent, and predictable order. The rhythmic heartbeat of a feeding black hole is a signature of predictable violence, but some cosmic phenomena refuse to be categorized at all. Drifting in the deep radio sky are structures so strange they were named exactly what they are: odd radio circles. These ORCs are not stars, not galaxies, not the remnants of any known explosion. They are perfect, enormous rings of radio emission, and they have no obvious source at their center. They are cosmic smoke rings on a scale that dwarfs entire galaxies, and we have no idea what is blowing the smoke. Their discovery was a product of the modern era of big data astronomy. While processing vast radio sky surveys from the Australian Square Kilometre Array Pathfinder, astronomers spotted a handful of these bizarre circular objects. They are faint but unmistakable, glowing only in the radio part of the spectrum. When researchers looked at the same patches of sky with optical, infrared, or X-ray telescopes, they saw absolutely nothing. The circles were invisible, ghosts in the radio static. Their size is the first staggering detail. Each ORC spans about 1 million light-years across, roughly 10 times the diameter of our Milky Way. If one were visible to the human eye, it would appear in our sky as wide as several full moons. Yet, for all their immensity, they are incredibly thin and uniform, like a bubble skin stretched across the void. The central region inside the ring is dark, a void of radio emission, and crucially, there is no bright object, no galaxy cluster, no obvious engine sitting at the heart of these gargantuan halos. The theories to explain them are as wild as the objects themselves. One leading idea is that they are the aftermath of a titanic shockwave. Perhaps they are the expanding shells from a gargantuan stellar explosion, a supernova on steroids occurring in a galaxy we simply cannot see. Or maybe they are the reverberation from a merger of two supermassive black holes, a gravitational wave event so powerful it sent a spherical tsunami through the intergalactic medium, lighting up a ring as it passed. Another possibility links them to known but rare galaxies called starburst galaxies, where stars are born at a ferocious rate. The combined winds from millions of supernova in such a galaxy could blow a colossal bubble into space, and we might be seeing the radio-bright rim of that bubble edge on, like looking at the circular lip of a glass. Yet each of these explanations runs into problems. The energy required to create a shockwave 1 million light-years wide is almost incomprehensible, far exceeding even the most powerful known events. And if it were a bubble from a central galaxy, where is the galaxy? The dark centers of the ORCs remain stubbornly empty. This void at the heart of the mystery has given rise to truly speculative ideas. Could an ORC be the throat of a wormhole, a tunnel in space-time viewed from the end? Theoretically, the extreme warping of space at such a structure might produce a ring-like emission. Or are they the imprints of collisions between universes in a vast multiverse, bruises left on our cosmic fabric from an encounter with another reality entirely? While fascinating, these are ideas of last resort, entertained only because the more conventional explanations keep falling short. The true nature of odd radio circles is a humbling reminder of how much we still have to learn. They represent a completely new class of astronomical object, something never predicted by our models. Their discovery tells us that the radio universe, which we thought we were mapping with increasing clarity, is still full of profound surprises. They are like finding a new type of cloud in an atmosphere we thought we understood, a cloud larger than continents and made of a substance we cannot identify. For now, they simply hang in the data, perfect circles of silent radio noise, drawing a giant question mark on our maps of the deep sky. The universe's first 3 minutes should have been a predictable recipe. In the searing heat just after the Big Bang, protons and neutrons fused to create the first atomic nuclei, a process called Big Bang nucleosynthesis. This cosmic cookbook successfully predicted the amounts of hydrogen and helium we see throughout the cosmos with stunning accuracy, a cornerstone proof of the Big Bang theory. But for one ingredient, the math fails spectacularly. The universe appears to be missing lithium. This is not a small accounting error. It is a fundamental deficit that challenges our understanding of the universe's birth. According to the precise calculations of Big Bang nucleosynthesis, the primordial fire should have forged a specific amount of lithium-7, an isotope of the third lightest element. When we look at the oldest stars in our galaxy, those pristine relics that formed from nearly pure Big Bang material, we should see this predicted lithium abundance etched into their atmospheres. Instead, we find only about 1/3 of the expected amount. The lithium is simply not there. This discrepancy is known as the cosmological lithium problem, and it has persisted for decades, resisting every conventional fix. It suggests a gap in our knowledge, a piece of physics from the universe's first moments that we have not yet accounted for. One line of investigation looks inward to the stars themselves. Could these ancient stars have somehow destroyed or hidden their original lithium? Stars like our Sun are known to slowly burn lithium in their outer layers, but the oldest stars are far cooler and less massive, with calm outer atmospheres where lithium should be preserved like a fossil. Some theories propose that unknown mixing processes could have dragged surface lithium down into the hotter stellar interiors, where it was fused into other elements. Others suggest these stars might have planet-like rocky cores that settled lithium out of their atmospheres billions of years ago. Yet, even with these stellar scenarios, the uniformity of the deficit across many different ancient stars makes a purely astronomical explanation feel contrived. The more tantalizing possibility is that our model of the first 3 minutes is incomplete. Perhaps unknown particles, like certain types of dark matter, were present and interacting during those initial nuclear reactions, subtly altering the fusion pathways and reducing the final lithium yield. Or maybe the density of the early universe was not perfectly uniform in ways our equations have not captured. Some physicists have even explored the idea of nuclear reaction rates that differ slightly from the laboratory values we use in our calculations, though these have been measured with great precision. The lithium problem is a quiet but profound crack in the foundation. It tells us that while the broad strokes of the Big Bang are undoubtedly correct, the fine details of that first forge may still hold secrets. Every ancient star we observe with its lithium deficiency is a messenger from that primordial dawn, carrying a chemical signature that says our story of creation, for all its success, is not quite finished. We are left with a universe that followed the recipe almost perfectly, but for one missing pinch of cosmic salt. Black holes present us with a logical dead end, a place where physics as we know it breaks down into a singularity of infinite density. But what if we have been misreading the cosmic menu? A radical, speculative idea suggests that what we call a black hole might not be a hole at all, but a star made of something even more exotic than dark matter, a star made of dark energy. This theory, known as the gravastar or gravitational vacuum star, proposes a structure so strange it could rewrite the rules of stellar collapse and solve some of the most vexing paradoxes in physics. The problem with the traditional black hole model lies in its heart, the singularity. This is a point where all the collapsed star's mass is crushed into an infinitely small, infinitely dense pinprick, a place where the laws of general relativity cease to function. It is a mathematical warning sign that our theory is incomplete. Furthermore, the event horizon, the point of no return, creates the infamous information paradox. According to quantum mechanics, information about what falls into a black hole can never be truly destroyed, yet according to general relativity, anything crossing the event horizon is lost forever to the outside universe. These two foundational pillars of physics give contradictory answers, a conflict that has troubled physicists for half a century. The dark energy star is a bold attempt to sidestep this entire mess. In this model, when a massive star reaches the end of its life and collapses, it does not crush itself into a singularity. Instead, at the very last moment, its core undergoes a phase transition like water freezing into ice. The matter transforms into a new state, a bubble of dark energy. Dark energy, remember, is the mysterious force causing the universe's expansion to accelerate. It possesses a powerful negative pressure, a kind of cosmic repulsion. In the heart of a gravastar, this repulsion perfectly balances the immense inward crush of gravity, preventing total collapse. The result is a bizarre object with no singularity and, crucially, no true event horizon. From the outside, it would look almost identical to a black hole. It would have an incredibly strong gravitational pull, bending light and trapping orbits, but instead of a one-way membrane, the surface of a gravastar is a thin, ultra-dense shell of ordinary matter, frozen in a state just at the point of forming a horizon. Inside that shell is not a hole but a vast, expanding pocket of dark energy, a miniature cosmos contained within a star. The implications are profound. Without an event horizon, there is no point of no return. Information is not lost forever. It could, in principle, interact with the inner dark energy realm or even eventually leak back out, solving the information paradox at a stroke. It replaces the terrifying infinity of a singularity with a bizarre but physically possible state of quantum vacuum. Of course, this is highly speculative theoretical physics. No one has observed a gravastar, and proving its existence would be extraordinarily difficult, as its external appearance mimics a black hole so closely. The subtle differences might appear in the way it rings like a bell when disturbed, or in the precise shadow it casts, details future generations of gravitational wave observatories and ultra-precise telescopes might one day detect. The dark energy star represents a thrilling direction of thought. It shows that when faced with a logical impossibility like a singularity, the human mind can conceive of alternatives that sound like science fiction. It asks us to consider whether the darkest objects in the sky are truly holes, or if they are something else entirely, something filled with the same repulsive force that is stretching the entire universe apart. It is a reminder that sometimes, to solve a cosmic paradox, you must be willing to imagine a star that is not a star, made of energy that is not light, holding back a collapse that never quite finishes. The chemical history of our galaxy is written in starlight, a ledger of elements forged in stellar furnaces and scattered by explosions. Yet among the oldest pages of this ledger, we find entries that do not add up. Drifting in the vast, sparse halo of the Milky Way are ancient stars so pristine they are almost pure hydrogen and helium, relics from a time before planets, before life, before most elements even existed. These are the metal-poor stars, and their atmospheres are cosmic time capsules. But some of these capsules hold a baffling contradiction. They are stamped with the signature of elements they should not possess. Standard stellar archaeology tells a clear story. The first generation of stars, called Population 3, were behemoths made only from the primordial soup of hydrogen and helium from the Big Bang. They lived fast, burned hot, and died young in colossal supernova, polluting the cosmos with the first heavy elements like carbon, oxygen, and iron. The next generation of stars, Population 2, formed from this newly enriched gas. Their metal content is a direct record of those first explosions. The rule is simple: the fewer metals, the older the star. So when we find a star like SMSSJ 2329 43.3-02272.6, a star with an iron content over 10 million times lower than our Sun's, we know we are looking at a near-pristine artifact. Its atmosphere should be a simple recipe reflecting the output of just one or two of those first supernova. But when astronomers read its spectrum, they found something astonishing: a significant amount of zinc and strontium, elements far heavier than iron. This is the anomaly. Creating elements heavier than iron requires a tremendous influx of neutrons, a process that typically happens in the slow, steady burn of aging stars or in the violent chaos of neutron star mergers, events that should come much later in a galaxy's life. They should not be present in meaningful quantities in a star this ancient. It is like finding a Stone Age tool made of stainless steel. The presence of these unexpected elements points to a progenitor, a first-generation star that died in a way we have never seen. The leading theory is that this was a special kind of supernova, a faint supernova with a fallback. Imagine a massive primordial star collapsing. In a normal supernova, the explosion blasts the star's outer layers, enriched with new elements, into space. But in this rare model, the explosion is weaker. The outer layers are ejected, carrying lighter elements, but the inner core, where the heaviest elements are synthesized, falls back onto the newborn black hole, trapped forever. However, in the moments before that final fallback, a powerful jet of material might be launched from the poles of the collapsing star. This jet, rich in neutrons, could rip through the surrounding layers, creating a brief, intense environment perfect for forging heavy elements like zinc and strontium through what is called the rapid neutron capture process. These newly minted heavy elements would then be launched into space by the jet, seeding the cloud of gas that would later form the anomalous star we see today. This star, therefore, is not just a relic. It is the offspring of a cosmic event that straddles two regimes, a partial explosion that failed to completely unbind its star, yet succeeded in manufacturing and launching exotic matter. It defies the clean categories of our chemical evolution models, forcing us to accept that the first stars did not all die the same way. Some may have whispered their demise with a complex, nuanced signature, leaving behind a chemical fingerprint that we are only now learning to decode. Each of these anomalous metal-poor stars is a singular clue, suggesting that the dawn of the elements was not a uniform blaze but a tapestry of strange and varied fires. That chemical fingerprint from the universe's dawn reveals a single, strange stellar death, but the ongoing light show from Tabby Star suggests a death or a construction happening in slow motion over centuries. Years of intense scrutiny have passed since its bizarre dimming patterns first ignited theories of alien megastructures, and the data has slowly, stubbornly, begun to point toward a more natural yet still deeply puzzling culprit. The James Webb Space Telescope, with its unprecedented infrared eyes, recently delivered a crucial piece of evidence. When it observed Tabby Star, it found that the dimming was far more pronounced at shorter, bluer wavelengths than at longer, infrared ones. This is the classic signature of dust. Tiny particles, smaller than a grain of smoke, scatter and block blue light more effectively than red, exactly as our sunsets turn the sky orange. The alien megastructure hypothesis, which envisioned solid, opaque panels or swarms, would block all colors of light equally. The color-dependent dimming strongly favors a natural, dusty explanation. So the mystery is solved then, not even close. Identifying dust as the agent of the dimming is like a detective finding a smudge of soot at a crime scene. It tells you something burned, but it does not tell you what burned, how it burned, or why the fire behaved in such an erratic, dramatic way. The central defiance of logic remains intact. What is producing this immense, irregular cloud of dust? The leading natural model is a colossal, fragmented swarm of comets or the debris from a catastrophically shattered planet, orbiting in a long, elliptical path. As this cloud of rubble passes closest to the star, it heats up, releasing more dust and causing a deep dimming event. The irregular timing could be explained by the cloud breaking into further fragments, creating a chaotic, clumpy distribution. Yet the scale required is mind-boggling. To cause the 22% dimming observed, this swarm would need to contain more mass than all the asteroids in our entire solar system combined, a truly monstrous amount of debris. Furthermore, such a violent event should have left a huge, diffuse infrared glow from all the warm dust, which we simply do not see enough of. The dust is there, but not in the abundance the simplest models predict. This gap between evidence and explanation is where the imagination and legitimate scientific curiosity continues to flourish. The dust could be a byproduct, not the main event. Imagine an advanced civilization that is not building a solid Dyson sphere, but something more subtle, like a vast array of energy collectors or habitats. Even a partially built structure, or one undergoing constant maintenance and expansion, would generate industrial debris, a cloud of fine dust and fragments drifting in orbit. From our distant vantage point, this technological pollution would look, in many ways, indistinguishable from a natural comet swarm. It would scatter light in the same way. The irregular dimming patterns could then reflect construction schedules, orbital adjustments, or even periods of intense activity, a kind of cosmic industrial cycle. This speculative leap keeps the idea alive not because it is likely, but because it is not yet impossible to rule out. Tabby Star endures as a cultural icon of cosmic mystery precisely because of this lingering ambiguity. The data narrows the possibilities, yet the most satisfying natural explanations still strain credulity with their own extreme requirements. It presents us with a choice between two breathtaking narratives: a solar system undergoing a cataclysm of almost biblical, unnatural proportions, or a civilization so advanced its greatest works mimic the dusty detritus of a natural disaster. Both possibilities stretch the mind. For now, the star continues its silent, flickering performance, a reminder that sometimes the most profound discoveries are not the answers we finally receive, but the depth of the questions we are finally brave enough to keep asking. The universe's ledger of ordinary matter has never balanced. We can tally up all the stars, galaxies, and visible gas we see, and compare it to the amount of normal matter or baryons that must have been created in the Big Bang according to the precise recipe of the cosmic microwave background. The numbers are off by a lot. Nearly half of all the atoms, protons, and neutrons that should exist in the present-day universe are simply missing from our inventories. This is not dark matter, this is the stuff we are made of, and it has vanished. The hunt for these missing baryons is one of cosmology's greatest detective stories, and the prime suspect is hiding in plain sight, woven into the largest structure in existence. Between the great clusters and voids, the universe is not empty. It is threaded with a vast, delicate architecture known as the cosmic web, a network of filaments made of incredibly hot, diffuse gas. These filaments are the superhighways of the cosmos, where gas flows between galaxy clusters, but they are so tenuous and so scorching hot, millions of degrees, that they emit almost no visible light. They are ghostly threads, nearly impossible to see directly. To find the missing matter, astronomers had to learn to see the shadow it casts. They turned once again to the cosmic microwave background, the ancient afterglow. As this primordial light travels for billions of years to reach us, it passes through the entire universe, including these hidden filaments of hot gas. When the light encounters this searing plasma, a subtle interaction occurs. High-energy electrons within the gas can give the passing photons a tiny boost of energy, a phenomenon known as the Sunyaev-Zeldovich effect. This leaves a specific, faint fingerprint on the microwave background, a slight distortion in its temperature. It is an incredibly weak signal, like trying to hear a single instrument tuning in a stadium during a roaring concert. To detect it, scientists needed to combine observations from thousands of pairs of galaxy clusters, knowing that the filaments of the cosmic web should stretch between them. By stacking the microwave data along these predicted bridges, they could amplify the faint whisper of the effect. The results were a revelation. The distortions were there. The missing baryons had been found, not in bright stars or glowing nebulae, but in a pervasive, seething ocean of gas that fills the spaces between the galaxies. This warm, hot intergalactic medium is the final reservoir, the hiding place for the universe's ordinary atoms. This discovery completes a fundamental chapter in our cosmic story. It confirms that the matter forged in the first moments did not disappear. It was simply too hot and too spread out for our telescopes to see. The grand architecture of the cosmic web is not just a skeleton of dark matter. It is also laced with rivers of familiar atoms, a hidden circulatory system for the cosmos. Finding it required us to stop looking for light and to start reading the subtle shadows that the universe paints on its oldest canvas. While we map the hidden rivers of matter between galaxies, a far closer mystery tugs at the edges of our own celestial neighborhood. The orbits of the most distant known objects in our solar system are whispering a secret, a pattern that hints at the gravitational hand of something massive and unseen. This is the Planet 9 hypothesis, a bold proposal that a world larger than Earth, perhaps up to 10 times more massive, is silently orbiting the Sun far beyond Pluto. The evidence is not a photograph or a direct glimpse. It is written in the peculiar, clustered paths of a group of extreme trans-Neptunian objects, icy bodies in the distant Kuiper belt. These objects have elongated orbits that take them hundreds of times farther from the Sun than Earth. By all rights, their orbits should be randomly oriented, scattered like hands on a clock. Instead, astronomers noticed something deeply strange. The points in their orbits where they swing closest to the Sun, their perihelia, are bunched together in space. Even more telling, their orbits are tilted in a similar direction, as if they are all being shepherded or herded by a common gravitational influence. The odds of this clustering happening by pure chance are astronomically low, less than 1 in 10,000. It is as if you dropped a handful of marbles on a trampoline and they all rolled to the same corner, suggesting a heavy, unseen weight is warping the surface beneath them. That unseen weight, according to the mathematical models, is Planet 9. Its proposed orbit is immense, taking between 10 and 20,000 years to complete a single journey around the Sun. At its most distant, it would be over 20 times farther out than Neptune, a frozen giant moving through perpetual twilight. The search for this phantom world is a monumental challenge. It is predicted to be incredibly faint, reflecting only the barest glimmer of sunlight, and its vast orbital path means it could be almost anywhere in a huge swath of the sky. Astronomers are using some of the world's most powerful telescopes, like Subaru on Mauna Kea, to conduct a painstaking pixel-by-pixel survey of the likely regions of space. They are looking for the slowest of moving points of light against the fixed background of stars, a task akin to spotting a single, crawling ant on a football field at night using only a flashlight. The hunt has already ruled out large portions of the predicted orbit, narrowing the possible hiding places but not yet finding the prize. This absence has fueled alternative explanations. Some scientists propose the gravitational influence might not come from a single planet, but from the collective pull of many smaller Kuiper belt objects, a swarm whose combined mass could theoretically mimic the effect of one large world. Others have raised the possibility of a primordial black hole, a leftover fragment from the Big Bang with the mass of a planet but compressed into an object no larger than a grapefruit, its gravity warping the orbits just the same. While fascinating, these ideas are considered less likely than a planet, but they underscore how the anomalous orbits demand some kind of explanation. The implications of finding Planet 9 would be revolutionary for our understanding of the solar system's history. Its existence would strongly suggest it was not born in its current distant orbit. More likely, it formed closer to the Sun alongside the other giant planets, and was violently flung outward during the solar system's chaotic early days, a dramatic event that reshaped the entire outer planetary disk. Its discovery would rewrite the final chapter of our solar system's formation, adding a major character to a story we thought was complete. Conversely, if the search conclusively proves it does not exist, the mystery deepens exponentially. We would be forced to invent entirely new physics or dynamics to explain the orbital clustering, a puzzle with no easy solution. Whether a hidden giant or a ghostly signal of something even stranger, the clustered orbits in the deep freeze beyond Neptune are a profound reminder. They tell us that even in our own backyard, the map is not finished. There are still blank spaces large enough to hide worlds, and the gravity of the unknown continues to pull at the edges of everything we think we know. That hidden gravity at the edge of our solar system is a local puzzle, but the most urgent crisis in modern cosmology is a disagreement about the speed of everything. The final discovery on our list is not an object or a signal, but a number, a single, crucial value that refuses to stay still. Astronomers call it the Hubble constant, the rate at which the universe is expanding. For over a century, we have known the cosmos is stretching, carrying galaxies away from each other like raisins in a rising loaf of bread. Measuring how fast that loaf is rising should be one of the crowning achievements of science. Instead, it has become our greatest embarrassment, a disagreement so stark it is known as the Hubble tension. There are two primary and utterly reliable ways to measure this expansion rate. The first method looks back to the universe's infancy, to the cosmic microwave background. By analyzing the subtle patterns in this ancient afterglow with exquisite precision, missions like the Planck satellite can calculate the ingredients of the early universe, the amounts of dark matter, dark energy, and ordinary matter, and then run the cosmic film forward using Einstein's equations. This predicts how fast the universe should be expanding today. It gives us a very specific number. The second method measures the expansion directly in our modern universe. It uses cosmic mile markers called standard candles, most famously a type of exploding star known as a Type Ia supernova. These explosions have a known intrinsic brightness. By measuring how dim they appear from Earth, astronomers can calculate their exact distance. By then measuring how much the light from their host galaxy has been stretched to redder wavelengths, the redshift, they can see how fast that galaxy is receding from us. Combine distance and recession speed for many supernova, and you get a direct local measurement of the Hubble constant. Both methods are pillars of modern cosmology, backed by decades of refinement and Nobel Prize-winning work. Here is the problem: they do not agree. The early universe measurement from Planck suggests a relatively sedate expansion rate. The late universe measurements from supernova and other local probes insist the expansion is significantly faster. The discrepancy is not a small statistical fluke. It is now at a level of over 5 sigma, meaning the chance it is a random error is less than 1 in 3.5 million. The universe, according to its own history, is expanding about 5 to 10% faster today than the recipe from its birth says it should be. This is not a minor accounting error, it is a fundamental crisis. It is as if you carefully measured all the ingredients for a cake, baked it following the recipe exactly, but when you took it out of the oven, it was noticeably larger than the pan you put in. Something is wrong with our understanding of the baking process itself. The tension forces us to confront a universe that may be more dynamic and strange than our standard model allows. Perhaps dark energy, the force driving the acceleration, is not a constant as we have assumed. Maybe it has been strengthening over time, or it interacts with dark matter in ways we have not imagined. Could there be a new, unknown type of particle or radiation that flooded the early cosmos and altered its expansion history? Some have even speculated about the properties of the Big Bang itself, questioning if the universe is subtly lopsided or if we are living in a vast underdense region that is skewing our local measurements. Each proposed solution is radical, requiring us to rewrite chapters of the physics textbook we thought were complete. The Hubble tension is the sound of the foundation cracking. It is a clear, numerical signal that our beautiful, coherent model of the cosmos, the lambda cold dark matter model, is incomplete. This single number, this rate of expansion, is the most critical parameter in all of cosmology, and we cannot agree on what it is. The implications are profound. If the local measurements are correct and the expansion is truly faster, it means the universe is younger than we calculate from the early universe data. It reshapes timelines and reconfigures our past. More importantly, it is a beacon pointing directly to the new physics that must exist beyond our current understanding. This is not the end of cosmology, it is the exhilarating beginning of the next revolution. The tension is not a failure, it is an invitation. It is the universe presenting us with its final, and perhaps greatest logical defiance, a disagreement in its own diary that compels us to look deeper, to think harder, and to discover what truly lies in the dark between the lines of everything we think we know. These 30 cosmic whispers and shouts paint a portrait of a universe that refuses to be tamed by our logic. From the Great Attractor's invisible pull to the impossible galaxies seen by the James Webb Telescope, each discovery is a crack in the foundation of what we think we know. They are not isolated puzzles, but pieces of a vast, bewildering picture that reveals our scientific models as beautiful, yet profoundly incomplete, sketches of a reality far stranger than we ever dared to imagine. The cosmos is not a clockwork mechanism. It is a living, breathing enigma filled with phantom matter, geometric storms, and echoes of collisions with other realms. This journey through the illogical is a celebration of our own ignorance, a reminder that the greatest adventure lies not in the answers we hold, but in the mysteries that still hold us. So tell us, which of these 30 discoveries defied your sense of reality the most? Let the debate begin in the comments below. And if you are hungry for more journeys to the edge of understanding, make sure to subscribe and join us for our next exploration into the profound unknown. The universe is waiting, and its greatest secrets are still hiding in the dark.